In this video, we will go over the unimolecular nucleophilic substitution reaction, or we also refer to it as an SN1 reaction mechanism. So in the SN1 reaction mechanism, the reaction is a stepwise process in which the two-step, the loss of the leaving group, and the nucleophilic attack do not happen at the same time, but one after the other. The step that happened first is the loss of the leaving group to form the carbocation intermediate. So here in this case, here is our substrate. And the leaving group leave first to form the carbocation intermediates. And that's this step happened first. Once the intermediate carbocation is formed already, it is then followed by the nucleophilic attack, where the nucleophile come in to attack this carbon, and finally creating our product. So when we observe the kinetic of an SN2 reaction, this is what we observe. So here is our substrate, and our nucleophile is water. And when we perform this reaction, the product then becomes ROH and SX. So here in this case, the OH is replacing the X, and the X is then the leaving group. So when we vary the different types of substrate, this is what we observe. If we were to have a tertiary substrate, in this case, tertiary substrate with the bromine as the leaving group. And in another experiment, we vary another substrate. In this case, it is secondary substrate. And here is the primary substrate. And when we compare the rate of these three reactions, and we observe the following. Their relative reaction rate is 1 to 12 to 1 million, or 200 times. So we will then see the reaction rate is much faster when we have the tertiary substrate. So when the concentration of the substrate is double, we observe that the rate is double. And when we change the concentration of the nucleophile, for example, doubling the concentration of the nucleophile, we would then observe that the reaction rate is unchanged. So rate is not affected. Therefore, we would then see that the reaction is first order with respect to the concentration of the substrate, and the reaction is zero order with respect to the concentration of the nucleophile. So the overall rate of reaction equal to K multiplied by the concentration of the substrate. So here in this case right here, overall the reaction is then first order. And it is only affected by the concentration of the substrate, but not the nucleophile. So that's something we have seen. SN1 reaction mechanism is dependent on the concentration of the substrate. And the more substituted the substrate, the faster the reaction rate would be. And because the rate of reaction is dependent on only the concentration of the substrate, and this step right here, and because the step involves only one chemical entity in its transition state, this is then said to be a unimolecular reaction. And in fact, SN1 means the following. S means substitution, N is nucleophilic, and 1 here means unimolecular. It is unimolecular because the rate of the reaction is dependent on only one chemical entity, and that is the substrate, but not dependent on the concentration of the nucleophile. Energy diagram of an SN1 reaction. Below is the energy diagram of an SN1 reaction. So in this case right here, the first step in the reaction mechanism is the loss of the leaving group. And here would be that step right there. And once this is leaving up and breaking, then now we end up with our carbocation intermediate, and this is the intermediate, followed by the nucleophilic attack, and the step in here corresponds to the energy of the nucleophilic attack to finally give rise to the product. And we will then observe that the step, the loss of a leaving group step, is the step with the highest activation energy. So therefore, this is our rate determinant step. The nucleophilic attack in here do not require that much energy at all to happen. So the rate of the reaction is dependent on only the rate of the slow step, and that is the loss of the leaving group step. And this slow step is again called the rate determinant step. So here in this case right here, this clock right here kind of show us what is happening. So in this case right here, this is the slowest step, it have the smaller opening, and this step right here have a larger opening. How fast can the sand go from top to bottom is dependent on this slow step right here. But once this slow step can happen, then the step on the bottom with the larger opening can happen really quickly. So in this case, this is the rate determinant step, and that is the loss of leaving group step. So that is the rate determinant step in an SN1 reaction mechanism. Let us now investigate the effect of the structure of the substrate on SN1 reaction. So in the SN1 reaction, the rate of the SN1 reaction is highly dependent on the nature of the substrate. But this trend right here is opposite compared to the trend that we saw in SN2 reaction. So in SN1 reaction, the more substituted substrate, then the faster the rate of the reaction would be. So faster and slow in this case for SN1 reaction. We will observe the opposite trend had this been an SN2 reaction. And the reason why that happened is that in the SN1 reaction mechanism, steric of the substrate is not an issue because the nucleophile do not attack the substrate directly, but it waits for the carbocation to form first before the nucleophilic attack. Once the carbocation is formed already, it does not matter whether a primary, secondary, or tertiary, the nucleophile can come in and attack the carbocation very easily. So therefore, the nucleophilic attack, it does not matter at all. But what's important is the step that gives rise to the formation of the carbocation. So the rate is dependent on the stability of the carbocation intermediate. How fast we can form the carbocation, that is now our rate determinant step, and that also correlates to the step where the leaving group is broken up, because as the leaving group is broken up, that's how we will be able to generate our carbocation. And between these different types of carbocation, the tertiary carbocation is more stable. Therefore, it can form the fastest, and this is least stable. Because the formation of the tertiary carbocation is more stable, it can happen faster. Therefore, more substitute substrate undergo SN1 reaction much faster compared to the less substituted substrate. And here in energy diagram to actually explain that. So if we are comparing the SN1 reaction rate between a secondary substrate versus a tertiary substrate. So in the case of a tertiary substrate, the activation energy here is lower compared to a higher activation energy that we see here in the secondary substrate. So this is higher activation energy, and this is a smaller activation energy, and therefore can happen faster. And the reason why that this with the tertiary substrate that they have a lower activation energy is due to the stability of the intermediate. So this intermediate right here is more stable than this intermediate. So therefore, it do not require that much energy to get to this more stable intermediate. And here, let's now try an example draw the carbocation intermediate for this following SN1 reaction. So we're given an SN1 reaction and we are asked to then draw the carbocation intermediate. So here in this case, the leaving group have to leave first. That is the step that is needed in the SN1 reaction mechanism. And once that happens, we will be able to produce this carbocation. And this is the tertiary carbocation. And once that is formed already, the nucleophilic attack will then come in and attack this carbon, producing this product over here. So this is the loss of the leaving group. And this step is then the nucleophilic attack. Now, SN1 reaction would always happen in this order. First, the loss of the leaving group first, followed by the nucleophilic attack, not simultaneously as compared to what we have seen in the SN2 reaction mechanism. And now, let's analyze the stereochemistry control in SN1 reaction. SN1 reaction normally produce a racemic mixture. And if that is the case, it will then make SN1 reaction not as helpful or productive compared to an SN2 reaction. And the reason why that it will produce a racemic mixture is because in SN1 reaction, it involves the formation of a carbocation intermediate, which can then be attacked from either side equally, therefore leading to both the enantiomer that would get formed. So here's a diagram to explain this. So first, let's say we have this example and we do an SN1 reaction mechanism. So here in this case, the first step that will happen is then the loss of the leaving group. Once this leave already, we will now have a carbocation in here. And the next step would then be the nucleophile come in to attack this. Let's say now we add in a different nucleophile. Let's say the chlorine is the nucleophile. In this case, the nucleophile can come in and attack in this direction or in this other direction. Both of them can happen equally and therefore giving rise to a racemic mixture of product. So we will then get the product where the chlorine is added to the opposite side and becoming this product. PR stands for the propyl group. So this is the product that have the inversions of configuration. And if the chlorine were to attack from this side, we will then end up with this product. And this is the product that have the retention of the configuration, and they are the racemic mixture. So there's no stereochemistry control in the SN1 reaction mechanism. But in reality, there is usually a slight preference for the inversion of configuration product compared to the product that have the retention of configuration. And therefore, if we do not form exactly equal amount of both of the enantiomer, but more of one, slightly more of one over the other. And the reason why is as follows. When the leaving group leave to form this carbocation and this leaving group. So here is the formation of the carbocation right here. So because this is positive charge, the leaving group is now negative. It may interact with this positive charge right here due to attraction of opposite charges over a distance. And in this case right here, if we were to break up, initially the leaving group would then stand on this side. And now, after the nucleophile come into attack, it will be easier for the nucleophile to attack from this side compared to this side, simply because the leaving group is on this side, right over here. So because of steric in here. So therefore, we will form both of this product, but not with equal amount. So this one right here is slightly more than 50%, and this one is slightly less. but the differences is not that significant. And in the end, we can basically conclude that in SN1 reaction will produce a racemic mixture. However, notice that it's not exactly the same. Let's now try some of this problem right here. Predict the product of this SN1 reaction and then label the configuration of the product whenever relevant. So let's try the first few examples. So on this first one, NABR, it is an ionic compound. So when we dissolve this in solution to perform this chemical reaction, the bromine, this is our nucleophile. So in this case right here, this is an SN1 reaction mechanism. So first, the bromine will break up first, and what we would then produce would then be this intermediate. So please note that this carbon right now, it no longer becoming a chiral center. So initially, this is a chiral center. Once the leaving group breaks up already, this now become achiral. And because it is now achiral, the top part of this ring and the bottom part of this ring right here are roughly equal in steric. So therefore, the bromine can come in and attack either from the top or from the bottom. So in the end, we'll be making this product. So the bromine can attack either from the top or from the bottom, leading to both of this product. So this will be the product when the bromine attack from the top. And this product here will be the product when the bromine attack from the bottom. And we'll be forming both of this product, a racemic mixture. And a lot of time, whenever we have a racemic mixture, instead of drawing the two enantiomer, we can draw a dash, a wedge bond. We can draw a wiggle bonds. And whenever we have a racemic mixture being produced, instead of drawing both of the enantiomer, we can use the wiggle bond to draw the product. And that would then imply that both of the enantiomer gets formed. So here in this case, we would then be dashing this bond, Br, and the other one is the methyl group. But this is a wiggle bond, meaning it can either be on top or on the bottom. And now let's try number 2. So here in this case, what would be the product? And the product would then be the following. So the bromine with the chlorine here is the nucleophile. And that would then come in to replace the iodine. Because the first step that will happen is then when the iodine breaks off first to form the carbocation. So initially, we will be forming this carbocation. And now when we add in the chlorine can come in to attack either from the top or from the bottom. And we'll be making again a racemic mixture. So in this case right here, we can also draw this product this way and now say the word racemic. So when we say draw this product without specifying the chiral center and saying including the word racemic, we are then implying both of this product can get formed. And this will be another way of doing it rather than using the wiggle line. And on this next reaction, the product that we will produce would be where the sulfur come in to replace this. And now we have our methyl group over here and our SH. And again, we can now say racemic. And that will mean both of the enantiomer will get formed. Notice how this molecule right here is chiral. So the starting reactant is chiral, which then have optical activity to it. At this reaction to produce this product now is also chiral as well. However, it have no optical activity. The products being produced have no optical activity. And the reason is because we have a racemic mixture. A racemic mixture have no optical activity. And lastly, with this one, again, in this SN1 reaction mechanism, first the chlorine breaks up first to form this intermediate, followed by the nucleophile attack, where now this can come in to attack either from the top or bottom and creating a racemic mixture of different products. So we can draw as follow without specifying the stereochemistry and say the word racemic to imply that both of the product get formed.